In this video, we're going to do some dimensional change extension problems, kind of see a little bit more challenging look at this topic. And so to start off, we need to recap what we covered in the previous video, and that's the idea that when the side lengths of a figure are dilated by a scale factor of x, then the surface area will change by a scale factor of x squared. We're talking about square units, so that scale factor is going to affect the area twice, if maybe that's a helpful way of thinking of it. And then when the side lengths of a figure are dilated by a scale factor of x, then the volume changes by a factor of x cubed for the same reason. With volume, we're dealing with cubic units. So every time you change that scale factor, you're changing it 3 times in your volume. So let's kind of see some challenging examples of how this might look. And so we're going to start with the ratio of the surface areas of two similar solids is 36 to 49. Find the ratios of their heights. And so we can start by letting x represent the scale factor between the solids. But we got to remember that the scale factor relates to the linear dimensions such as the height, not the surface areas. Okay? And so if x is the scale factor, then the surface areas are related by a factor of the scale factor squared. In other words, if I started with my original surface area of 36, I can't do 36 times x equals 49 because that wouldn't be accurate. These are the surface areas and they're not related by the scale factor, they're related by the scale factor squared. So this would be the equation that you would need to set up to solve this. And so what I would do is I would then divide by 36 on each side. And then I would take the square root of each side of my equation. And this is your scale factor. Now, there's a few ways to think about this and a few ways to interpret this. So one thing that you could say is that if the scale factor is 7/6, then you could say that the small solid's height multiplied by 7/6 would give you the height of the larger figure. Or you could say that the ratio of heights is 6 to 7. It's a 6 to 7 ratio, okay? Now, another strategy for this type of problem, and I'll go ahead and show you the other strategy, it would be that if you started with kind of this ratio, this surface area ratio of 36 to 49, since it's the square of the scale factor that relates these, you could just take the square root of both of them, and you would get that same 6 to 7 ratio that we got over here. So either way of thinking about that will work. The ratio of the volumes, now we're dealing with volume, of two similar cones is 27 to 64. Find the ratio of the areas. So we're going to start by letting x represent the scale factor. I'm going to put this reminder on every problem. Remember that the scale factor relates the linear dimensions and not the volumes. And so we know that if x is the scale factor, the volumes will be related by a scale factor of x cubed. How this works itself out is like this. I'm going to take the volume of my smaller figure, which would be our 27, and you might be tempted to say 27 times some scale factor x is 64, but that is not the case, because the scale factor does not relate the volumes. The scale factor cubed relates the volumes. So if we were to solve this equation and figure out what the scale factor is, I would first divide by 27 on each side, and then I would take the cube root of each side of my equation. The cube root of x cubed is just x. I'm using the inverse operation of cube root to undo cubing this x. I hope that makes sense. And then if I cube root the left side of my equation, I have to cube root the right side of my equation. When you cube root a fraction, you're going to take the cube root of the numerator and the cube root of the denominator. And you get 4/3. So what this means to us is a couple things. This means the scale factor is 4/3. Now, what we got to be careful about is that scale factor doesn't relate the areas. This one asks us to do the next step and actually find the ratio of the areas. So what we know that previously, let's say we had this. Let's let A represent the surface area of the first figure, and let's let B represent the surface area of the second figure. You might be tempted to say the surface area of the first figure times 4/3 gives you the surface area of the second figure, but that is not the case. It's the scale factor squared. So we wouldn't multiply by 4/3. We would take that first figure and we multiply by the square of 4/3, which is 16/9 equals B. And so this says find the ratio of the area. So let's go ahead and kind of summarize our thinking here as a ratio. We could say that that first surface area times 16/9 gives us the second surface area. Or you could say that the ratio is 9 to 16. That would actually be our final answer. Now we can use kind of what I would call like almost our cheater method. If we knew that the ratio of volumes is 27 to 64, we could first find the ratio of the individual linear dimensions. And our way we do that is I would take the cube root of both sides of this ratio, and you would find out that, okay, the cube root of 27 is 3, the cube root of 64 is 4, and so kind of in how we got the scale factor of 4/3 here, you get that ratio of 3 to 4 here. But you got to keep in mind, this is the ratio of the linear dimensions, of the side lengths, or of the heights. What you would then have to do is to find the ratio of the surface areas. You would have to square both sides of this ratio, and you would get that 9 to 16 ratio that we're looking for. You can see those are both strategies for finding the same answer. All right, so in this problem, it doesn't say it, but let's assume these two figures are similar, that we have two similar rectangular prisms. On this one, it looks like it gives us this length is 16. It gives us this one is 12, and they give you the volume of the smaller figure, but the surface area of the larger figure. And first it says find the surface area of figure B. And so let's do like we've been doing, and let's let X represent the scale factor between the solids. And reminder, once again, I sound like a broken record, the scale factor relates to linear dimensions and not the surface areas. So what I could do is let's first find what the actual scale factor would be for those linear dimensions. I know that if we take our larger figure with its side length of 16 and we multiplied by our scale factor, it would give us the corresponding side length in our figure B, which would be 12. So 16 times some scale factor gives me 12. If I were to solve this by dividing by 16 on each side, we get x equals 12 over 16, which actually simplifies to 3/4. That means that is our scale factor. This relates to the linear dimensions. This does not relate the surface area that we're looking for. We're looking for surface areas, right? Now, what can we do here? Well, we know the surface area of our original figure is 608. So if I come up here, we have our original surface area of 608. I wouldn't want to multiply that by 3/4 to get my new surface area, because the 3/4 scale factor relates to the linear dimensions and not the surface areas that we're looking for. So instead of multiplying by 3/4, I'm going to multiply by 3/4 squared. So you could just punch this in your calculator as is, or you could change 3/4 squared to 9 over 16, which is what this is equal to. But whenever you actually put that in the calculator, you would find that the surface area of figure B, your smaller figure, is going to be 342 meters squared. Okay, so our strategy on the problems like this would be to solve for that scale factor first, and then just know that we're using the square of that scale factor to find our missing surface area. Now, we're going to use the same problem situation, but now we're actually going to find the volume of figure A. So I think on the previous one, we considered this our pre-image, and we multiplied by a scale factor to find this. We did 16 times x equals 12. Let's go the other direction this time, because it doesn't really matter. Let's consider this my pre-image, I guess. So let's say 12 times some scale factor x equals 16. Okay? If I were to solve this for x, which is our scale factor, I would divide by 12 on each side, and that's going to simplify to 4/3. And I think that kind of makes sense. In the previous problem, we did 16 times 3/4 to give us 12. So we can do 12 times 4/3 to give us 16. We're just kind of going this way now. Okay, so don't let that throw you off. And so what we know is we know the volume of the original figure, but we're trying to find the volume of figure A. Note it doesn't give us the volume anywhere. So what we can do is we can start with that original volume of 324. And you might be tempted to multiply by that scale factor of 4/3, because 12 times 4/3 is 16, but keep in mind that's for linear dimensions. We're now doing this same thing with volumes. And we know that volumes are not related by the scale factor, they're related by the scale factor cubed. So I would take this volume, multiply by the scale factor cubed to find the volume of figure A. Once I punch all those buttons into the calculator, you would get 768 cubic meters. And I believe that is the end of the lesson.